Hello everyone, my research topic is fairness-aware maximal clique enumeration, which aims at finding all cliques satisfying our definitions of fairness. We know community detection is really important nowadays, and an elementary model called Clique has had a wide range of applications in social networks, financial networks, and so on. However, past works only considered finding subgraphs satisfying the clique structure. They didn't take the attributes or vertices into account. In other words, they neglected the fairness. In machine learning field, researchers have proposed several conceptions of fairness to make sure the predictions or classifications are unbiased, like group fairness, individual fairness, and so on. Inspired by this, we start studying the fairness in subgraph mining. We proposed two definitions called weak fair clique and strong fair clique. We design algorithms to effectively find these fair cliques in the real-life graphs. We say mining fairness-aware maximal cliques has many applications because it can help revealing the structure information of graphs and finding out dense communities with certain constraints. For example, it can be used to identify research groups who work closely and also have diverse research topics, because the fair cliques have already considered the fairness over different research topics. Finding such fair cliques can help identify the groups of experts from diverse research areas to conduct a particular task. Also, it can be used in areas like advertising. We say everyone has his or her tags or preference in e-commerce. Abstracting the preferences into an attribute, then we can find the fair cliques meet the need of advertisement. So companies can select key opinion leaders within it. For both definitions, we use a threshold K to indicate the lower bound of vertices for every attribute, such that no attribute will be ignored, especially for those minorities. A weak fair clique is a maximal clique in which every attribute owns at least k vertices. Like in the left graph, the shaded vertices form a weak fair clique with k up to 3. A weak fair clique is also a normal maximal clique in a graph. Or we say we can get them by filtering all maximal cliques in the network. Clearly, the weak fair clique enumeration problem degenerates to the traditional maximal clique enumeration problem, which is NP hard. So finding weak fair clique is also NP hard. A strong fair clique is stricter than a weak fair clique, for it asking for absolute equality for attributes. Also, see the left graph. There shows a strong fair clique with 3 nodes of attribute A and 3 nodes of attribute B. The enumeration of strong fair clique is more difficult because they are not always traditional maximal cliques. They will appear in the middle nodes of a searching tree, which increases the difficulty of algorithm design. So next, I will introduce the algorithm design of our fair cliques. Both enumeration algorithms follow a 2-step frame. First, reduce the left vertices, and then perform clique enumeration, but the details are different. First, I will introduce the weak fair clique enumeration problem. Before that, I will briefly introduce the graph coloring problem, which aims at coloring all vertices such that no connected vertices have the same color. A best graph coloring problem is an NP-hard problem, so we use an approximate way to compute the colors of the vertices. Namely, we use the greedy coloring algorithm. Based on the color of vertices, we propose a definition called colorful degree. The colorful degree of a vertex U based on attribute AI is the number of the colors of U's neighbors whose attribute value is A. In this graph, for example, for vertex V1, it has two colorful degrees, dA equals 3 and dB equals 4. Once getting the colorful degree of a vertex, we can decide whether to prune it. We propose a definition called colorful K-core, which is a subgraph. In a colorful K-core, every vertex has a minimum colorful degree larger than K. If a vertex wants to be contained in a weak fair clique with threshold K, it must have at least K-1 neighbors with every attribute. According to this conclusion, we believe a K-fair clique should be included in a colorful K-1 core. The procedure of performing core decomposition procedure based on vertex minimum colorful degree is called colorful core. We use a queue to record the vertices and their minimum colorful degrees. By popping out the vertices whose minimum colorful degree is less than K, we update the colorful degrees of the remaining vertices. This process continues until no vertex is removed. After the pruning of graph, we start searching weak fair cliques. To accelerate the enumeration, we propose a vertex ordering method called colorful ordering. This way to get colorful ordering is familiar with colorful core. We use a priority queue to make sure the vertex with smaller minimum colorful degree has a smaller order. Equipped with colorful ordering, a backtracking procedure is used to find all weak fair cliques. In the searching procedure, we use 4 sets, R, X, C, and res. The set R represents the currently found clique, which may be extended to a weak fair clique. X is the set of vertices in which every vertex can be used to expand the current clique R, but has been already visited in previous search passes. C is a candidate set that can be used to extend the current clique R, in which each vertex must be neighbors of all vertices in R. And R is an answer if and only if both C and X are empty sets. Otherwise, we continue searching. We make use of the set R and C to check whether the search should be continued. Once we find the sum of vertices for any attribute is less than K, we prune the branch. Because we cannot obtain a weak fair clique, even if we add the whole set C into R. When it comes to strong fair clique enumeration, we first consider the situation when D equals 2, which means the graph only has 2 attributes, and then we expand it to the high-dimensional situations. In the 2-dimensional case, we propose a notion called fairness degree to help computing. Fairness degree is the largest number of groups from which we select the vertices so that the number of vertices with attribute A1 is the same as the number of vertices with attribute A2. We divide the neighbors of our vertex U into 3 groups called OA1 group, OA2 group, and the mixed group. If a color only contains vertices with attribute A1, then it belongs to the OA1 group. If it only contains attribute A2, then it belongs to the OA2 group. Otherwise, it belongs to the mixed group. Since the OA1 group and OA2 group can only contribute to one attribute, they are fixed. But mixed group can contribute to both groups. So we try to make the size of OA1 group equal with that of OA2 group by adding vertices in the mixed group. The process goes on like this graph. We first try to make the size of OA1 group equal with OA2 group by adding colors in mixed group. Then we divide the left part of mixed group into two same sides and add them to two groups. The final size of OA1 group or OA2 group decides the value of vertex fairness degree. Equipped with fairness degree, we perform core decomposition to get a fairness K-core. This process is similar with how we get colorful K-core. And in our paper, we prove that for a given parameter K, any strong fair clique must be contained in a fairness K-1 core of the graph. Similar with colorful ordering, we derive a fairness ordering to accelerate the enumeration. Different from weak fair clique enumeration, we use an attribute alternative selection way to enumerate all strong fair cliques. By selecting the vertices of every attribute one by one, we make sure the current clique can be controlled. The searching procedure admits an input parameter A5 to indicate the attribute value of the vertices to be selected in the current iteration. Since a strong fair clique may appear on the middle of a searching tree, if a clique itself satisfies the attribute constraints of strong fair clique, we check if this clique is maximal by invoking a procedure called isMaximal. We check whether more vertices can be added into the current clique. For cases d larger than 2, the algorithm is a little different, because both fairness degree-based core decomposition and ordering method cannot be used anymore. There will be too many combinations of mixed group, making it difficult to get the accurate fairness degree. So we use colorful degree-based core decomposition to prune the graph when d is larger than 2. Besides, we use a heuristic fairness degree to replace the accurate fairness degree to accelerate the searching. We call it heuristic ordering. In heuristic ordering, for every mixed group, we decide which attribute it will contribute to by counting the current attribute size. That is to say, for all the attributes a mixed group can contribute to, we find the one with the minimum color and assign this mixed group to it. This greedy way is consistent with our ideas of fairness. So the total algorithm looks like this. And next, I will introduce the behavior of our algorithms. We evaluate the pruning techniques, the running time of enumeration algorithms, the number of fair cliques, the scalability, and so on to show our efficiency. We use 4 real-world graphs: Wikitalk, the marker, Slashdot, and Flixter. Wikitalk is a communication network, and the others are all social networks. All these datasets are non-attributed graphs. Thus, we randomly assign an attribute to each vertex to generate attributed graphs, which will be used to evaluate the efficiency of all algorithms. In the evaluation of the pruning techniques, the colorful core and the fairness core methods reduce a great number of vertices compared to the original graph. From the graphs, we can see that, in general, fairness core consistently outperforms colorful core in terms of the pruning performance, especially for relatively small k values. As expected, when k goes larger, the number of remaining vertices becomes smaller. Additionally, we can also observe that the pruning performance of colorful core is slightly worse than that of fairness core for large k. This is because fairness core first invokes colorful core to prune unpromising vertices. Since colorful core is already able to prune a great number of vertices when k is large, Faieness core cannot further prune too many vertices after invoking colorful core. For the evaluation of weak fair clique enumeration, except for our new ordering technique, colorful ordering, we use two different orderings, BFS ordering and the VID ordering, to demonstrate our efficiency. As can be seen, the baseline algorithm only outputs the results on /dot and cannot terminate within the time limit on the other datasets. But the runtime of our weak fair clique enumeration algorithm decreases as K or D increases. Moreover, we can see that the runtime of weak fair clique enumeration algorithm is several orders of magnitude lower than that of baseline algorithm for a large K or D. For a large K, weak fair clique enumeration algorithm can prune many vertices by the colorful K-core-based pruning technique, and the search space can also be reduced during the backtracking procedure. For a large D, the number of weak fair cliques decreases with an increasing D, thus reducing time overheads. The colorful ordering also behaves great compared to other orderings. Similar observations can also be seen in the experiment for strong fair clique enumeration, that our fairness-based ordering outperforms other orderings. The baseline algorithm of invoking BK algorithm, then filtering, has to enumerate all cliques in the graph. And that's why it didn't perform well, especially when K or D is large. But our strong fair clique enumeration algorithm avoids this problem by graph pruning and the vertex ordering. This figure shows the number of fair cliques in the graphs. Clearly, there are significant numbers of fair cliques in each dataset. In general, the number of strong fair cliques is larger than that of weak fair cliques, which is consistent with our analysis, since a weak fair clique often contains a set of strong fair cliques. The scalability testing, randomly picking 20% to 80% of the edges, and evaluate the runtime of all the proposed algorithms. These results demonstrate the high scalability of the proposed algorithms. Finally, we conduct a case study based on the collaboration network DBLP to show a real-life usage of our definition of fair clique. We extract a subgraph DBCS from DBLP, which contains the authors who had published at least one paper in the database data mining and artificial intelligence related conferences. We illustrate some fair cliques we found in this graph. This case study indicates that the weak fair cliques and the strong fair cliques show the scholars of different research areas who cooperate with each other, and further reflects the closeness of different research areas. That is, the closer these areas are, the larger fair cliques will be. There are several future directions deserved to be further investigated. First, the proposed models are based on the concepts of clique, which might be too strict for some real-life applications. So we might relax the clique model used in our definitions and apply other models like K-trust to define the fairness-aware cohesive subgraphs. Second, the proposed pruning technique is mainly based on the colorful K-core. We may develop other pruning technique like colorful K-trust-based pruning technique. Since K-trust is often much denser than K-core, such a pruning technique may be more powerful than our colorful K-core-based technique. So this is how our ideas working, and thanks for listening.